Today we discuss multivariate normal distribution. Multivariate normal distribution. Last class we have seen the univariate normal distribution. This is the formula. If x is a random variable, then 2 pi sigma square e to the power minus half x minus mu by sigma square minus infinite less than x less than plus infinite. So, the PDF multivariate normal PDF is characterized by mu and sigma. Mu and sigma, that is the population parameter. Okay. We want the counterpart of it in the multivariate domain when x, that univariate x is converted to capital X, which is your x1, x2, xp, and univariate mu is no longer univariate, it will be a very mean vector mu1, mu2, mu p, and similarly univariate sigma square will no longer be univariate, it will be a multivariate covariance matrix. P cross P. So, that means we want something by multivariate normal distribution, we want something which is f x in terms of n variable number p and mean vector and covariance matrix. How do we go about it? Now, how to do it? That is the discussion today. So, today we will discuss bivariate normal density function, multivariate normal density function and properties of multivariate normal density function, and if time permits we will go for statistical distance and constant density contours. So, the univariate PDF is this. You want to visualize its multivariate counterpart. So, let us consider a bivariate case. You see this slide, in this slide you see that there are two variable x1 and x2 and probability density, that is joint density, that f x1 and x2, x1 and x2. Okay. So, this is what is given in figure. So, you see that you are getting a bell shape, but in 3 dimension you are getting, because there are first 2 dimension for the 2 variable values and third dimension is the density values. And if you take one more dimension, it is difficult, you cannot visualize. Getting me? Suppose there are 3 variables with density, we cannot visualize pictorially. Now, as I told you, our objective of the first part of today's lecture is we want to develop this. This is our objective. This one is our objective. So, in order to do so, we will follow a systematic but simple path. Okay. Suppose you think that you have 2 variables x1 and x2, which we are saying a bivariate case. So, our x is x1 and x2, that is why, and my mu is that mean vector mu1 and mu2, and your covariance matrix will be 2 by 2, sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2. I hope that there is no problem with you. in this one nomenclature. So, we assume something here, you see the slide here. In the slide you see the top figure, that here is a scatter plot. Now, what you can say about the two variables x 1 and x 2, seeing the scatter plot, are they correlated or there is no correlation? Is it something like a circle you are getting or ellipse? There is no pattern. So, you see that it is an ellipse type of thing, but there is no correlation. So, we want to simplify our derivation without correlation. So, that means what I mean to say, our sigma 1 2 is 0 or rho 1 2 is 0. If there is no correlation, then what will be the joint density? Suppose x 1 and x 2, multiplication of the marginal density of the two. So, x 1 cross x 2. Okay. Now, all of us know that f x equal to 1 by root over 2 pi sigma 1 square as it is x 1 e to the power minus of x 1 minus mu 1 by sigma 1 square. Then similarly, for f x 2 also, that is the second variable, you can write 2 pi sigma 2 square e to the power minus of x 2 minus mu 2 by sigma 2 square. We can write this, and definitely here x j less than greater than minus infinitive to less than minus infinitive, j equal to 1 2, two variables you have taken. So, if I multiply this, what we are getting? We are getting like this 1 by, there is one quantity called 2 pi. So, 2 pi you are getting 2 by 2, 2 pi into 2 pi square root 2 by 2. Then another one, what you are getting, sigma 1 square and sigma 2 square, also sigma 1 square sigma 2 square to the power half you are getting here. Yes or no? And then I am coming to the exponent part, e to the power minus half, and all of us know that e to the power a into e to the power b equal to e to the power a plus b. So, we can write this one like this, x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square. We can write this. So, essentially what is happening here, that in when I go for that univariate normal or bivariate normal with no dependent structure, you are having two component in the density function. One is the constant part, another one is the exponent part. Two part is there. One part is component, that is the constant, another part is the exponent, means e to the power something. And when you are making the joint distribution here also, you are having also two part, this and this. The general structure for the multivariate normal distribution univariate that remains same. What is the difference? Difference will come in the to the components, the values will be different. So, we found out that if x 1 and x 2 are independent, then our structure is like this. Okay. Now, let us see that we want to derive this constant part as well as exponent part from the population parameter, that is what we have. We have mu equal to mu 1 into mu 2, mu equal to mu 1 mu 2, not mu 1 mu 2, mu 1 mu 2, and we have sigma is sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2. This one you can write now, sigma 1 1 equal to sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square. Okay. So, if I make something like this determinant of sigma, what is the determinant of sigma here? Sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square, its determinant. And you know that determinant will be this cross this minus this cross this. So, this one is sigma 1 square, sigma 2 square minus sigma 1 2 square, correct. Now, you see that what we have assumed in the earlier demonstration, we say sigma 1 2 equal to 0. Just for the sake of simplicity, we have taken like this, sigma 1 2 equal to 0. So, if sigma 1 2 equal to 0, then determinant of sigma is nothing but sigma 1 square, sigma 2 square. So, if I make square root of this, then this is the determinant or square root of the determinant. And if this is the case, then the constant part, what is the in case of our independent bivariate density function, we found out that constant part is 2 pi 2 by 2 sigma 1 square sigma 2 square to the power half. Now, this I can write like this 2 pi 2 by 2 determinant of covariance matrix to the power half. Okay. Now, suppose you have one more variable. That means, suppose you have taken 3 variables now, like x is x1 2, x2 and x3, and you have also consider that your sigma is sigma 1 square 0 0 0 sigma 2 square 0 0 0 sigma 3 square. What we are assuming? We are assuming that all the variables are independent. Then what will happen again? F x1, x2, x3, it will be f x1 into f x2 into f x3. So, in the similar way you multiply, ultimately your constant term will be 1 by 2 pi, now 3 variables are there by 2, then sigma 1 square, sigma 2 square, sigma 3 square to the power half. You see, if you take determinant here, what are you getting here? It will be sigma 1 square, sigma 2 square, sigma 3 square. So, that means determinant to the power half is sigma 1 square, sigma 2 square, sigma 3 square to the power half. So, if you now increase it to p variables, so ultimately your sigma, that dimension will change, and sigma to the power half will take care of one part of the constant. So, if I go by p variable now, my constant will become like this 1 by, you see that when there are 2 variables, it is 2 by 2. When there are 3 variables, 2 pi to the power 3 by 2. So, when there are p variable, it will be p by 2. And whether it is 2 variable or 3 variable or p variable case, ultimately this quantity will be replaced by determinant of covariance matrix to the power half. So, with one assumption here, that we are considering independent variables, we proved this is the case. Now, what will happen to your constant exponent term? So, in 2 variable case, we found out that the exponent term x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square. So, we say this is the exponent term. This is the exponent term, this portion is exponent term. So, it is x, you see that x1 minus mu 1, that is mean subtracted, divided by its standard deviation, that square. So, now create one, suppose x minus mu transpose, no, I'll explain from the univariate case, that will be better. So, univariate case f x 1 by root over 2 pi sigma square e to the power minus of x minus mu by, this is the case you have seen. Now, take the exponent one. So, your exponent is minus half, I am writing x minus mu sigma square to the power minus 1 x minus mu. Is it not this one? Is it not minus of x minus mu by sigma square? You see, x minus half is there, minus half, x minus mu, x minus mu, x minus mu square divided by sigma square. So, sigma to the power inverse. Now, if you go for the multivariate case, what will happen? Your x is replaced by capital X, mu is replaced by bold mu, sigma square will be replaced by sigma, correct. Now, in matrix multiplication, what will be the square? Transpose that matrix, x transpose x, that is the square term. So, we are basically making here square. So, we want this. So, that is why what I mean to say, in multivariate domain, the exponent can be written like this, x minus mu transpose sigma square is replaced by capital sigma to the power minus 1 x minus mu. That from univariate normal distribution, we have taken the exponent part, and we are saying that if we go in same manner to the multivariate part, our resultant quantity will be this for the exponent. Is it so? Can we prove now? Can we do like the same thing for x equal to x1 and x2 two variable case, mu equal to mu 1 and mu 2, and sigma equal to, we have taken already sigma 1 square 0 0 sigma 2 square, because we are independent case we want to prove first, because we know under this condition what will be the distribution multivariate normal density function, that is known. So, then you write down minus half. So, x minus mu transpose. So, that means this is x 1 minus mu 1, x 2 minus mu 2, because x minus mu is x 1 minus mu 1, x 2 minus mu 2, 2 cross 1, it will be 1 cross 2. Okay. Now, your what do you want? Sigma 1 square 0 0 sigma 2 square, this inverse. Then what you, so that is 2 cross 2. Then x 1 minus mu 1, x 2 minus mu 2, this is your 2 cross 1. So, what is the resultant quantity? 1 cross 2, 2 cross 2, 2 cross 1, it is a 1 cross 1. This will give you 1 cross 2, this will give you 1 cross 1. It is a density that exponential to the power this constant value, you will be getting some value, density will be calculated. Okay. Now, what is the inverse? How do you calculate the inverse? Suppose if A is a matrix like this, A11, A12, A21, A22, how do you compute the inverse? 1 by adjoint by determinant. So, A inverse, it is adjoint of A by determinant of A. Now, adjoint is the transpose of the cofactors. Adjoint is transpose of cofactor of A divided by determinant of A. So, if this is the case, our A is nothing but this one, sigma 1 square 0 0 sigma 2 square, that is what is our sigma. Now determinant, already we have seen the determinant is sigma 1 square and sigma 2 square, multiplied by these two. Now what will be the cofactor of this? Cofactor is, if you suppose I want to know cofactor of sigma, here suppose in A case you see cofactor means, suppose you want to see the cofactor of this, then you have to cross this the corresponding row and column. What is left, that is the cofactor, but the sign conversion will be there. So that means cofactor means, so for A I j the cofactor will be minus 1 I plus j, correct, in the remaining portion, whatever the remaining portion, remaining part of the matrix, that will be the case. As we have taken 2 by 2 cross, so ultimately what will happen, one row and one column crossed means only one item will left. So it is our case is easier. Then cofactor of this we can write, first one is minus 1 to the power 1 plus 1, that is 1 plus 1. Then what is remaining here, sigma 2 square, suppose you cross this and this, sigma 2 square will be there, and see it is 0 and it will be also 0, and sigma 1 square will be this. So our cofactor is sigma 2 square 0 0 sigma 1 square. What will be its transpose? Same, because these two elements are 0. So now transpose of cofactor of sigma, this is again coming the same thing, because row and column interchange, it is symmetry 1 0 0 sigma 1 square. Then what is my inverse? Inverse is that is the cofactors, mean 1 by determinant you write down first, sigma 1 square and sigma 2 square, that is the determinant, sigma 2 square 0 0 sigma 1 square. Okay. Now calculate this one. My calculation is minus half our x1 minus mu 1, x2 minus mu 2, then inverse is coming like this, 1 by sigma 1 square sigma 2 square, sigma 2 square 0 0 sigma 1 square, then multiplied by x1 minus mu 1 and x2 minus mu 2. Suppose if I do this portion first, what you will get? You will get minus half x1 minus mu 1, x2 minus mu 2, 1 by sigma 1 square sigma 2 square. This is 2 cross 2, this is 2 cross 1, you will be getting 2 cross 1. This into this plus this into this. So it is basically sigma 2 square x1 minus mu 1. Then this into this plus 0, then 0 plus again sigma 1 square x2 minus mu 2. Now let me bring this one this side, later on we will manipulate, sigma 1 square sigma 2 square. So if you multiply this 1 cross 2 and 2 cross 1, you will be getting 1 cross 1. So this into this plus this into this, you see what is happening, sigma 2 square x1 minus mu 1 square, because x1 minus mu 1 x1 minus mu 1, plus sigma 1 square x2 minus mu 2 square. So if you divide these two by sigma 1 square sigma 2 square, what you will get, what you will be getting? You will be getting like this, minus half, then it will be sigma 1 minus mu 1 by sigma 1 square plus x2 minus mu 2 by, correct, x1 minus mu 1 by sigma 1 square, this one, and you have seen that we have found out earlier also, this is f x 1 cross f x 2, this we found out like this. This one only you found out. This one you found out, you just check. I am showing that earlier when we have multiplied the 2, what we got here, 1 by 2 pi 2 pi to the power 2 by 2 sigma 1 square sigma 2 square half, then minus 1 by 2 x 1 minus mu 1 by sigma 1 square, this one, and here what are you getting? Here same thing you are getting. So, what I mean to say, although this is not a derivation, this is the other way proof, that what we are saying, that means I can write for a bivariate case, I can write my bivariate normal distribution like this. This is the case. You can write like this. Okay. But if, and it is true for multivariate case also, then what will happen ultimately? Multivariate case x 1, x 2, x p, then it will be 2 pi to the power p by 2 determinant of this, then e to the power minus half x minus mu transpose, this is the case, and you have to write minus infinite x j infinite, j equal to 1 to p. This is our multivariate normal distribution. We say multivariate normal density function defined. Okay. Now, what will be the bivariate density normal density function when your matrix is like this, covariance matrix is like this, sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square. That means there is covariance. This is the case. What will happen? Can you not find out this determinant of this is our sigma 1 square, sigma 2 square minus sigma 1 2 square. So, this can be written like this, sigma 1 square, sigma 2 square minus rho 1 2 sigma 1 sigma 2 square. Covariance is correlation times the standard deviations. So, we can write this one sigma 1 square sigma 2 square 1 minus rho 1 2 square. Okay. And what will be your inverse here? So, inverse will be 1 by determinant. So, 1 by determinant, let me keep this one only, then sigma 1 square sigma 2 square minus sigma 1 2 square into, we know that transpose of the cofactor. So, I will take this, so it will be sigma 2 square, then what will be this plus this will be minus sigma 1 2 minus sigma 1 2 sigma 1 square. Then what is my exponent part? Half x minus mu transpose, x minus mu transpose sigma inverse x minus mu, which is equal to minus half x 1 minus mu 1 x 2 minus mu 2 x1 minus mu1 mu2, then 1 by sigma 1 square sigma 2 square minus sigma 1 2 square into sigma 2 square minus sigma 1 2 minus sigma 1 2 sigma 1 square times x1 minus mu1 x2 minus mu2. Correct. So, if you further manipulate, what will happen? This equal to minus half x1 minus mu1 x2 minus mu2. Then I want to multiply the last two parts, so I am writing like this: sigma 1 square sigma 2 square minus sigma 1 2 square into this one. You see, this is 2 cross 2 and this one is 2 cross 1. So, this multiplied by this plus this multiplied by this multiplied by this plus this multiplied by this. So, if we write like this, what will happen here? Sigma 2 square into x1 minus mu1 minus sigma 1 2 into x2 minus mu2. So, that is coming from this part, row column. Second one will be minus sigma 1 2 minus sigma 1 2 come here. We are multiply this with this. So, x1 minus mu1 and then plus sigma 1 square, your when you are saying sigma 1 x2 minus mu2. So, that is your matrix you are coming. So, this is the first row, this is the second row. So, it is 2 cross 1. So, then minus half into sigma 1 square sigma 2 square minus sigma 1 2 square you keep here. Then now you are multiplying this into this. So, multiply this is 1 cross 2, 2 cross 1 you will get 1. So, this into this plus this into this. So, what you are getting then? You are basically getting sigma 2 square x1 minus mu1 and x1 minus mu1, that is square, minus what you are getting, this into this. So, sigma 1 2 into x1 minus mu1 and x2 minus mu2. So, this into this over second column versus your second row. So, it will be minus sigma 1 2 x1 minus mu1 x2 minus mu2 plus sigma 1 square x2 minus mu2 square. That is the totality. So, if I further manipulate this, what I can write, sigma 1 square sigma 2 square minus sigma 1 2 square, then this is sigma 2 square x1 minus mu1 square minus 2 sigma 1 2 x1 minus mu1 and x2 minus mu2 plus sigma 1 square x2 minus mu2 square. If you divide this the within bracket quantity by sigma 1 square and sigma 2 square, what will happen? Minus 1 by 2 1 by sigma 1 square sigma 2 square minus sigma 1 2 square. So, I am dividing the entire thing by sigma 1 square and sigma 2 square, I am taking common. Then what will happen, this one x1 minus mu1 by sigma 1. See, sigma 2 is already there, sigma 1 square we have taken, sigma 1 I am keeping here, this minus 2 sigma 1 2, then divided by, you write sigma 1 and sigma 2 here. Can we not write like this, this equal this x2 by this. See, sigma 1 cross sigma 2 square you have taken here, plus you can write down x2 minus mu2 by sigma 2 square. What is this quantity? Sigma 1 2 by sigma 1 sigma 2, that is rho. So, I can write like this, minus half sigma 1 square sigma 2 square, and you have already seen sigma 1 2 square equal to sigma 1 square sigma 2 square into rho 1 2 square. So, you take common here, 1 minus rho 1 2 square, then this quantity is x 1 minus mu 1 by sigma 1 square minus 2 rho 1 2 x 1 minus mu 1 by sigma 1 x 2 minus mu 2 by sigma 2 plus x 2 minus mu 2 by sigma 2 square. So, this quantity, this will be cancelled out. Okay. So, if I see this versus the independent case, you will very easily find out now. If I put rho 1 2 equal to 0, this one will become 0. So, then this is x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square, and what you have, and here also rho 1 2 will be 0. So, that is 1 by minus half. So, that means the resultant quantity will be, if I put rho 1 2 equal to 0, my quantity is coming this one minus half x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square. Okay. So, this is the exponent part. Clear? So, that means what I mean to say, that in the reverse way also we proved that yes, this quantity is following the distribution, required distribution what we have thought of. Now, question comes, what is this? What is the shape of this? Ellipse. Correct. Now, see this diagram. This very important concept here. See, this is my equation, and we have started with this. We said this is the scatter plot of x 1 and x 2, and it resembles that there is no dependency between the two variables. That means covariance is 0, and we assume sigma 1 2 equal to 0. So, that means this one is nothing but this ellipse. What is coming here? This ellipse. So, that means if I just write down this one, what you are getting, you see that what I will do now, I will draw a line like this, but it will be a curve. So, it is basically coming like this. Got it? Here is some confusion. So, when you plot this x 1 and x 2's, that exponent part, you are getting an ellipse. When? Anytime you can get an ellipse, because this one is also an equation of ellipse. Please keep in mind, this is the in 2-dimensional general equation of an ellipse. So, if I want to plot this, what will happen to my figure? Your now depending on rho 1 2.
So, this I think origin is at mu 1 mu 2.
Yes, origin is at mu 1 mu 2. You see this figure, that is origin also at mu 1 mu 2. Data is given in such a manner that 0 is the origin, that mu 1 mu 2. Origin is mu 1 and mu 2. This is your mu 1 and mu 2. What will happen if you take the general equation? General equation means this one. So, depending on the row value, that row 1 2 value, is it positive, is it negative, is it 0. If it is 0, this is the diagram. This side, or you it may, because this side, see, in here the major axis of the ellipse lies along x 2 axis. The reason is the variability along x 2 is more. They are independent. That is why the major and minor axis of the ellipse go along the original x 1 and x 2 axis, and along x 2 axis the major axis lies, because the variability along x 2 is more and variability along y 2 is less, sorry, along x 2 is more, variability along x 1 is less. If variability along x 1 is more, then but they are independent, then your ellipse will become like this. Keep in mind they are independent. When row 1 2 is greater than 0, it will be, so x 1 increases, x 2 increases like this. So, it will be like this, inclined, because the major and minor axis of the ellipse are not parallel to the original x 1 and x 2 axis. So, as this one is increasing, this is also increasing. Other way, when it is less than, it will be just reverse. It will go to this level. Okay. But in one of the slide, I think I have shown you this picture, that my x 1 and x 2 is like this, my data is like this. It is a circle. This is also a bivariate case. So, this is also independent case. The question is this sigma 1 and sigma 2. In this case independent, but sigma 1 square equal to sigma 2 square. Okay. How do you know this axis? I know the ellipse. What is this value? Suppose this is the, first of all the direction, second one the value. How do you know all those things? Let us see some of the slides here. This is multivariate. Okay. So, let us see this one first. I will come back to this how to determine the axis and length, all those things. So, what I request to all of you, in order to understand the axis, you have to know little bit of matrix. What is this? Eigenvalue, eigenvector. So, eigenvalue and eigenvector. I will show you next class eigenvalue and eigenvector, then axis, the all those things. And now, from see one example. A process is characterized by two variables, that is, S process is designed to produce laminar aluminum sheet of length x 1 and breadth x 2 with the following population parameters. This and these are the population parameter. obtain its bivariate normal distribution. This is the answer. I am sure you will be able to find out this one. From the beginning, if you start the way we have described, if you start in the same manner, you will be ultimately ending with this answer. Okay. Come to properties. That multivariate normal distribution has certain very useful properties. Multivariate normal distribution, that we will denote next henceforth, it is MND. Multivariate normal distribution, which is we say NP, mu and sigma. It has many useful properties. Some of the useful properties I am describing now. You see the first property. If x is multivariate normal, then all the variables individually are univariate normal. Very obvious. That means, if x is, there are x1 to xp and they simultaneously multivariate normal, then x1 is also univariate normal, x2 is univariate normal, xp is also univariate normal. That means, what I mean to say, that this one where mu is mu1, mu2 to mu p and sigma is, I am writing sigma 1 square, sigma 2 square, sigma p square, and these components are also there. Any one, if I say the xj, this will be your univariate normal with mu j and sigma j square, j equal to 1 to p. So, that means that sigma j will be coming from here, that sigma j square. Okay. This is your first property. What is the second property? If x is multivariate normal, then any subset you take, that will be multivariate normal. Mean by this, what do we mean? We mean that suppose my x is this, x1, x2, xq, xp. What I create? I will create two subsets, that is x1, x2, that is big x1, x2. So, then this will be, this x1 is q cross 1 and x2 is p minus q cross 1 vector. Then what I want to say, we want to say that x1 is q variable vector. So, it will be multivariate with q dimensions, and what will be the mu, that is mu and sigma. What you will do? I am writing mu q and sigma q. If I write, what will be the mu? That first mu, because first q variables you have taken. What will be the sigma q? Sigma is now sigma 1 1, sigma 1 2, like sigma 1 q, sigma 1 p. Similarly, here sigma 1 q, then somewhere sigma q q, then sigma q p, then sigma 1 p, that sigma p p. So, you have created a subset with q variables. So, that means, what is happening here now? This is your sigma q. Okay. And mu case is mu 1, mu 2, mu q, mu p. So, this is your mu q. So, that means, if you take a subset and you know the parameters, for those, that subset of parameters you consider and find out it distribution, that will be multivariate normal distribution. The third distribution is very useful, third property. Third property is very useful. You see what is written. If x is multivariate normal, linear combination of x j is univariate normal. This property can be exploited like anything in your research. What does it mean? It means that suppose I will first create a vector like this, a1 all constant ap, some weights. My x is x1, x2, xp. Then this one is 1 cross p, this is p cross 1. So, what is the linear combination? Linear combination is yes or no? Obviously, because this will give you a1 x1 plus a2 x2 like ap xp. What it is says that this property says that what will be the expected value of ATX? It will basically AT, expected value of x will be AT and mu. This is nothing but A1 mu 1, A2 mu 2, AP mu p. And what will be your variance of this A transpose x? This will be your A transpose sigma A. You can prove it also like writing like this. So, A transpose sigma A, it is 1 cross P, P cross P, P cross 1, resultant is 1 cross 1. So, then the linear combination will follow univariate normal with A transpose mu, A transpose sigma A, that is our variance part. Okay. Now, the fourth property says that instead of one linear combination, if you make two linear combination, what is happening here? You just see, in one linear combination we have taken like A1, A2, we have taken AP. These are the weights. Instead of this, I am creating another one like this, A11, A12, A1p, A21, A22, A2p. Suppose AQ1, AQ2 dot AQP. What is happening now? And if I find out, so this one is my 1 to P, so this is P cross Q. This one is P cross 1. So, now if I make like this A transpose X, what will happen then? This will be your Q cross P and this will be your P cross 1. So, you will be getting something called Q cross 1, whereas in one linear combination A cross T is basically 1 cross 1. So, that means Q cross 1 means you are ultimately creating this one Q cross 1, A 1 1 x 1, A 1 2 x 2 like this, A 1 p x p for this, A 2 1 x 1 plus A 2 2 x 2 plus A 2 p x p. So, like this, A q 1 x 1, A q 2 x 2 plus q p x p. So, everyone will be this. If I take one combination, that is univariate normal, take this one second univariate. So, that means all linear combination univariate, but collectively what we are saying, collectively they will be multivariate normal. So, that means this quantity, this will be as q linear combination you have made, this into definitely what will happen, A sorry capital A transpose mu, then A, just check this transpose part, you have to check what is A here. A is P cross Q and this one is Q, na? Q. So, that means what we want, this will be Q cross Q. If I write like this, I think it will write. In books maybe they have written in the other way around, just that part you check. Ultimate aim is as it is Q variable vector, A transpose X is Q variable vector. So, the variance component will be order of Q cross Q and mean component will be order of Q cross 1. Column vector definitely. Okay. So, these 4 properties are important, and you see that when you calculate x bar in univariate case, when you calculate x bar, that is what? That is linear combination of multivariate observations. N observations are there, 1 by n into x one. So, equal weight. So, then what will be the distribution of x bar? All those, this univariate normal, that is why the sigma square by n is coming there. So, all those things, and here we will be seeing not that x bar only, it will be a big x bar, that means mean vector for the sample means, basically. Getting me? So, next class I will explain you that statistical distance. Okay. So, thank you very much.